The universe whispers its greatest secrets through the fabric of space and time. We often think of gravity as a silent, invisible force, but it is actually a voice. This is the secret language of gravity, a cosmic narrative written in ripples and waves. By the end of this journey, you will understand how to listen to the stories of colliding black holes and the birth of the universe itself. We will explore how a passing gravitational wave subtly changes the very shape of reality, and what these messages can tell us about the deepest cosmic mysteries. What does it mean to live in a universe that is constantly speaking to us? This fabric of reality is not a static stage but a dynamic, living entity. For centuries, we pictured space as a void and time as a separate, steady river. Then came Albert Einstein, who wove them together into a single concept he called space-time. Think of it not as empty nothingness, but as an immense, invisible trampoline sheet, stretched taut and incredibly flexible. This is the canvas upon which the universe paints its story. The revolutionary idea at the heart of Einstein's general theory of relativity is that mass and energy press down on this fabric, telling it how to curve. A planet or a star creates a depression, a well in the cosmic trampoline. Then the curved geometry of that well tells other objects how to move. This elegant interplay is the true essence of gravity. It is not a mysterious force reaching across emptiness, but a natural consequence of moving through a landscape shaped by mass. As the physicist John Wheeler so perfectly summarized, space-time tells matter how to move, matter tells space-time how to curve. Picture a bowling ball placed on that trampoline. It creates a deep, sloping indentation. Now, roll a marble near it. The marble does not get pulled by an invisible string. It simply follows the curved path created by the bowling ball's weight. This is the dance of our solar system, the reason planets orbit stars. They are simply following the invisible contours of space-time carved out by the star's immense mass. Understanding this cosmic fabric and its gentle curves is like learning the very first letters of gravity's alphabet. It is the calm, predictable script of the heavens. But what happens when this fabric is not just curved but violently shaken? The language becomes far more dramatic, and the messages it carries are from the most cataclysmic events in the universe. Yet even Einstein, the architect of this new cosmic vision, wrestled with its most dramatic implication. Just a year after completing his theory of general relativity, he performed a calculation that seemed to predict something astonishing. His own equations whispered to him of ripples. They suggested that if you could take the fabric of space-time and shake it violently, that disturbance would not stay put. It would propagate outward, a wave traveling at the very speed of light. He called these distortions gravitational waves. Imagine the last ripple from a stone dropped in a still pond, but instead of moving across water, this wave is a traveling distortion of space itself, a rhythmic stretching and squeezing of the cosmic dimensions. The source of such a wave must be a mass undergoing a dramatic change in motion. An electric charge creates a light wave when it jiggles. In the same way, a massive object, like a pair of stars orbiting each other, should create a gravitational wave as it accelerates through space. But here was the true challenge, and the reason for Einstein's own lingering doubt. Unlike a simple radio antenna that can broadcast in all directions, the mathematics showed that gravity waves have a quadrupole nature. This complex term simply means that to create these ripples effectively, a system's shape must be changing in a very specific, asymmetric way. A perfectly spherical star expanding and contracting uniformly would be silent. But a dumbbell spinning end over end, or two stars whirling around one another, is constantly changing its quadrupole moment. It is this cosmic wiggling that efficiently radiates power away as ripples in space-time. For decades, this prediction was seen as a beautiful but utterly inaccessible piece of mathematical theory. The waves, if they existed at all, would be unimaginably faint, their signal vanishingly small. Einstein himself wondered if they were merely a mathematical artifact, a ghost in the equations without physical reality. He had given science a prophecy, a clue to a secret language. But for half a century, there was no one who could build an instrument sensitive enough to even attempt to listen. For half a century, Einstein's ripples were a ghost in the machine, a beautiful idea just beyond our grasp. Then, on September 14, 2015, the universe finally spoke. At the Laser Interferometer Gravitational Wave Observatory, a signal arrived. It was not a long, drawn-out note, but a quick, rising chirp that lasted less than a second. This tiny blip in the data was the death cry of two colossal black holes, each over 30 times the mass of our Sun, performing their final, violent dance over 1 billion light-years away. As they spiraled inward at nearly the speed of light and merged into a single, more massive object, they shook the very fabric of space-time, sending a ripple across the cosmos that finally reached Earth. To hear this whisper, LIGO had to achieve the most precise measurement in human history. The observatory's 2-4-kilometer-long arms are arranged in an L shape. A laser beam is split and sent racing down each tunnel, bouncing off mirrors to return and recombine. In perfect silence, the light waves cancel each other out. But when a gravitational wave passes through, it does something extraordinary. It literally stretches space in one direction and squeezes it in the perpendicular direction. For that fleeting moment, one arm becomes infinitesimally longer than the other, disrupting the laser light and creating a detectable signal. The change in length LIGO measured was smaller than 1/10,000th the diameter of a proton. It is the equivalent of measuring the distance to our nearest star, Proxima Centauri, and detecting a shift in that distance the width of a human hair. One scientist described the moment they saw the data as a feeling of utter awe, a profound realization that we were no longer just looking at the universe, we were listening to it. This was not merely a discovery, it was a transformation. Humanity had grown a new sense, unlocking the ability to hear the cosmos and understand its most violent secrets. That faint chirp was more than just a sound, it was a message. Gravitational waves are cosmic messengers, and the information they carry is encoded directly into the very shape of the ripple itself. Think of that waveform, that squiggle of data from LIGO, as a sealed letter from 1 billion light-years away. Unlike light, which can be blocked by cosmic dust or absorbed by gas, gravitational waves travel to us almost completely unimpeded. They pass through matter as if it were not even there. This gives them a unique passport to the most hidden and violent places in the universe. We can now receive bulletins from the very heart of a collapsing star or from the chaotic maelstrom just outside a black hole's event horizon, regions forever cloaked in darkness to traditional telescopes. So what is written in this cosmic code? The waveform is a detailed fingerprint of the cataclysm that created it. By reading its subtle contours, scientists can decode the masses of the objects that collided. They can measure how fast those objects were spinning, like figuring out the rotation of a dancer from the pattern of their footprints. The signal even contains a precise measurement of how far the wave traveled to reach us, giving us a new ruler for measuring cosmic distances. It is all there, a complete forensic report of a violent event. This is similar to how seismologists on Earth study the ripples from an earthquake. By analyzing how seismic waves travel through our planet, they can deduce the structure of Earth's deep interior, layers we can never hope to visit. Gravitational waves are our seismographs for the cosmos. They allow us to feel the vibrations of space-time itself, revealing the hidden architecture and the most energetic processes of the universe in a way light alone never could. This new sense provides a pristine stream of information, completely untainted by its journey across the cosmos. That distinctive chirp from a billion light-years away is a complete story told in 3 distinct acts. It begins with the inspiral, a long cosmic courtship. 2 black holes locked in a mutual orbit slowly lose energy with every rotation. They radiate that energy away as gravitational waves, tightening their dance and accelerating as they spiral inward. This phase produces a wave that steadily rises in both frequency and amplitude, a rising tone that signals the impending collision. Then comes the merger itself, the climax of the event. This is the moment the 2 singularities become one, a violent and chaotic upheaval of space-time that lasts for only a few milliseconds. The waveform here is not a smooth curve but a complex burst, the literal sound of space-time itself being torn and rewoven. Finally, there is the ring-down. The new single black hole is born misshapen, like a bell that has been struck hard. It vibrates, shedding its asymmetries in a series of fading oscillations, a final sigh as it settles into a perfect, silent sphere. The entire signal, from the first rising note to the last quiver, is a direct translation of the black hole's properties. The frequency of the waves at the moment of merger is exceptionally revealing. A higher-pitched final chirp points to a system with a greater total mass because more massive objects orbit faster before they collide. It is like listening to a musical instrument. A massive double bass plays a much deeper note than a tiny violin. By reading the pitch and the shape of the waveform, scientists can weigh the black holes with astonishing precision, even from across the universe. These catastrophic events are more than just spectacular shows. They are the ultimate testing grounds for Einstein's theory. The gravitational forces near merging black holes are unimaginably strong, warping space-time to its absolute limit. By comparing the observed signal to the predictions of general relativity, we can check if the theory still holds true under such extreme duress. So far, it has passed every test. Each black hole collision we detect is a lesson in the brutal grammar of a new cosmic language, teaching us how matter and energy behave when the universe turns up the volume to its maximum setting. But the cosmic orchestra is not limited to black holes. Some of the most fascinating signals come from the duets of neutron stars. These are the ultra-dense, city-sized corpses of massive stars that went supernova. A single teaspoon of neutron star material would weigh billions of tons. When 2 of these incredible objects orbit one another, they also emit a rising chirp of gravitational waves, but the finale of their cosmic dance is profoundly different. Unlike the silent merger of 2 black holes into darkness, the collision of neutron stars is a spectacular, multi-sensory fireworks show. The gravitational wave signal itself carries a unique signature, a subtle fingerprint of the star's immense gravity and internal structure. As the stars spiral closer, their gravitational fields exert powerful tidal forces on each other, stretching and squeezing them. This tidal deformability leaves a distinct imprint on the gravitational waveform, a tiny wobble in the signal that acts like a cosmic X-ray. It lets scientists peer deep into the heart of a neutron star and probe the nature of the matter inside. This is matter crushed to densities and under pressures so extreme they cannot be recreated in any laboratory on Earth. Is the core a sea of free quarks, a perfect fluid, or a solid crystalline surface? The gravitational wave signal holds the answer. The full power of this new way of listening was proven in August 2017. The LIGO and Virgo observatories detected a long, rising chirp from a pair of merging neutron stars. Just 2 seconds later, satellites in space observed a brilliant flash of gamma rays from the exact same patch of sky. For the first time, we had both heard and seen the same cosmic event. This event, named GW170817, triggered a global campaign. Astronomers around the world pointed every major telescope at the source, witnessing the aftermath in visible light, X-rays, and radio waves. They saw the glow of a kilonova, an explosion that forges heavy elements like gold, platinum, and uranium. That single event confirmed that the gold in your jewelry was likely forged in the violent crucible of colliding neutron stars. This was the true birth of multi-messenger astronomy, a field where we no longer rely on just one sense. We can now hear the ripple in space-time and simultaneously see the flash of light, allowing the different languages of the universe to tell one coherent, magnificent story. Beyond the clear chirps of individual collisions lies a far grander and more subtle sound. It is the collective whisper of the entire cosmos, a low hum that has been ringing since the dawn of time. This is the stochastic gravitational wave background. Imagine standing on a shore and hearing the steady roar of the ocean. You are not listening to a single wave, but to the combined effect of countless, indistinguishable ripples crashing together from across the vast sea. The universe creates its own version of this cosmic noise. It is the superposition of every gravitational wave that has ever been generated, from billions of binary black hole systems spiraling in the darkness, from the hypothetical vibrations of cosmic strings, and perhaps even from the primordial tremors of the Big Bang itself. These signals are all jumbled together, their individual voices lost in a chorus so ancient and diffuse that it forms a permanent, underlying vibration in the fabric of space-time. To hear this hum, we need a detector of unimaginable scale, one that uses the galaxy itself as its instrument. Scientists are turning to the most reliable clocks in the universe, pulsars. These are the rapidly spinning cores of dead stars, beaming out radio waves with the metronomic precision of atomic clocks. By creating a network, a pulsar timing array, astronomers monitor these cosmic lighthouses across the galaxy, looking for a telltale sign. As the faint gravitational wave background washes through the galaxy, it ever so slightly stretches and compresses the space between us and these pulsars. This creates minuscule, correlated shifts in the arrival times of their pulses, a rhythmic delay and advance across the entire network. Finding this pattern is like trying to detect a single note in a symphony hall by listening only for the subtle vibrations it causes in every chair. The quest to detect this background is a search for the universe's oldest radio station, one that began broadcasting in the first fractions of a second after creation. Tuning into this signal would open a window to an era before the first stars were born, allowing us to hear the echoes of the universe's very first tremors. This quest for the universe's oldest hum leads us back to the very beginning, to a moment almost lost to time. In the first sliver of a second after the Big Bang, the cosmos is thought to have undergone a fantastically violent growth spurt called inflation. Space itself expanded faster than the speed of light, blowing up a subatomic speck into something macroscopic in an unimaginably short time. And in that furious expansion, the seeds for everything we see today were sown. The vacuum of space, even when empty, is not truly still. It seethes with quantum fluctuations, tiny particles and energy fields constantly flickering in and out of existence. During inflation, these tiny, random quantum jitters were stretched to an astronomical scale. Think of a tiny wrinkle on the surface of a rapidly inflating balloon. As the balloon grows enormous, that tiny wrinkle becomes a vast, continent-sized ripple. In the same way, those microscopic quantum fluctuations were imprinted across the entire universe, becoming the slight variations in density that, over billions of years, gravitationally collapsed into galaxies and clusters of galaxies. But there is another, even more profound consequence. These violent fluctuations did not just affect matter, they shook the very fabric of space-time. They generated the very first gravitational waves, primordial tremors that have been ringing through the cosmos ever since. These are not the waves from black hole collisions, but something far more ancient. They are the fossil imprint from the birth of the universe, a direct recording of its first chaotic moments. Detecting this specific background would be like finding a pristine audio recording of the first cry of the cosmos. How could we possibly hear such an ancient whisper? The most promising method involves looking at the oldest light in the universe, the cosmic microwave background. This afterglow from the Big Bang fills all of space, a snapshot of the universe when it was just 380,000 years old. As this primordial light traveled through the vibrating space-time of the early universe, the primordial gravitational waves would have left a subtle mark on it, a specific pattern of polarization known as B modes. Finding this faint, swirling fingerprint in the ancient light is the holy grail for many cosmologists. It would be direct, smoking gun evidence for cosmic inflation. The energy scales involved in that first fraction of a second are almost beyond comprehension. Probing this era with gravitational waves would allow us to study physics at energies 1 trillion times higher than what we can achieve at the Large Hadron Collider. We would be testing our theories of the universe at the most extreme conditions possible, right at the boundary where gravity and quantum mechanics must finally meet. This is the ultimate goal, to read the very first chapter of gravity's cosmic story, written in the faintest of tremors from the dawn of time. Is Einstein's theory of gravity the final word, or is it merely the best chapter we have read so far in a much larger book? Gravitational waves are now our most powerful tool for answering this, subjecting general relativity to tests of unimaginable severity. Every chirp from a black hole merger is a cosmic experiment, probing gravity in regimes where matter is crushed into singularities and space-time is warped to its breaking point. Scientists perform these tests by comparing the precise shape of the observed wave to the shape predicted by Einstein's equations. So far, the theory has passed with flying colors, but the search for even the tiniest crack in its foundation is relentless. One crucial test concerns speed. General relativity demands that gravitational waves travel at the speed of light. When the neutron star merger was detected in 2017, the gravitational wave signal arrived at Earth almost simultaneously with a burst of gamma rays. After a journey of 130 million years, their arrival times were virtually identical, confirming that gravity does indeed move at light speed. This rules out a whole class of alternative theories that predict different speeds. Another test lies in the very texture of the waves themselves. Einstein's theory predicts that gravitational waves should have only 2 polarization modes. Imagine the fabric of space being stretched and squeezed in a specific cross pattern. But some alternative theories, including those that try to weave quantum mechanics into gravity, predict up to 4 additional polarizations. Searching for these extra modes in the data is like listening for a faint, unfamiliar accent in gravity's voice, a hint of a deeper grammar we do not yet understand. Finally, there is the ring down. The fading vibrations of a newborn black hole must perfectly match the damped oscillations predicted by relativity. Any deviation, any extra echo or unexpected frequency would suggest that the black hole is not exactly the simple object we believe it to be. It could be a sign of exotic physics at the event horizon, or even a fingerprint of the long-sought quantum nature of space-time itself. Each new detection sharpens these tests. We are not just confirming an old theory, we are stress testing it at the absolute limits, ensuring that the dictionary we are using to decode the universe's messages is perfectly accurate. The day we find a discrepancy will be a revolution, the moment we realize gravity has been trying to tell us something even more profound all along. Detecting a ripple in space-time requires an instrument of almost impossible sensitivity. The heart of this effort is the laser interferometer, a device that transforms a tiny stretch of space into a signal we can see. At facilities like LIGO, this concept is scaled up to an epic size. Imagine two pipes, each 4 kilometers long, arranged in a perfect L shape. Inside these pipes, a near-perfect vacuum is created, a space emptier than the void between planets. This is to ensure that the lasers traveling down these tunnels meet nothing but the mirrors at each end. The principle hinges on the behavior of light waves. A single laser beam is split in two, with each half sent racing down an arm. They bounce off the mirrors and return to recombine. When the arms are exactly the same length, the returning light waves are perfectly in sync. Their peaks and troughs align and they reinforce each other, but this setup is intentionally tuned for cancellation. The waves are shifted so that a peak from one meets a trough from the other, and they cancel out, resulting in darkness at the photodetector. This perfect silence is the instrument's resting state. Then, a gravitational wave passes through. It does not push the mirrors. Instead, it subtly warps the geometry of space itself. For a fleeting moment, one arm becomes infinitesimally longer while the other becomes shorter. The laser light in one arm now has a slightly longer path to travel. This tiny mismatch, smaller than 1/10,000th the diameter of a proton, disrupts the perfect cancellation. The light waves no longer cancel each other out perfectly, and a flicker of light appears at the detector. That flicker is the whisper translated into data. The true challenge is not just measuring this shift, but isolating the instrument from a world that is constantly shouting. Every footstep, every distant earthquake, even the rumble of ocean waves on a faraway coast, creates vibrations that would drown the cosmic signal. To combat this, the mirrors are not rigidly fixed. They are suspended like ultimate pendulums, with a series of sophisticated filters that act as a multi-stage shock absorber, damping out the Earth's constant shuddering. The lasers themselves present another fundamental limit, the Heisenberg uncertainty principle. At this incredible precision, the quantum nature of light introduces a faint hiss of random noise, photons jostling the mirrors in an unpredictable quantum dance. To push past this standard quantum limit, scientists employ a remarkable trick called squeezing. They manipulate the quantum properties of the laser light itself, essentially quieting its fluctuations in one aspect at the expense of another, sharpening the instrument's hearing. This entire apparatus, a symphony of vacuum, laser, and suspension, is a monument to human ingenuity. It is a machine built to measure the unmeasurable, to feel the vibrations of the cosmos on a scale that defies belief. We have stretched our technology to the edge of the possible, all to answer the faintest call from the void. This global effort to listen to the cosmos relies on a synchronized chorus of observatories scattered across the planet. The original LIGO detectors in Washington and Louisiana were joined by Virgo in Italy, and later by Kagra in Japan, with a new observatory, LIGO India, planned for the future. Why is this international network so vital? A single detector might pick up a promising signal, but it could just as easily be a local tremor, a truck rumbling on a distant highway, or some other terrestrial glitch. A signal is only trusted as a true message from the cosmos when it is seen almost simultaneously by multiple detectors, separated by thousands of miles. This simple act of confirmation turns a maybe into a definitive discovery, but the network's true power goes far beyond simple verification. The tiny differences in the arrival time of a gravitational wave at each location are the key to unlocking the source's cosmic address. Imagine you are standing in a large, open field with your eyes closed, and you hear a single clap of thunder. You would have a very hard time figuring out where the sound came from. But if you had two friends standing far apart from you, and you all compared the exact moment you heard the clap, you could triangulate the position of the lightning strike. This is precisely how the global detector network operates. A ripple in space-time washes over the Earth, reaching one observatory a few milliseconds before another. By analyzing these minute-time delays across the global array, scientists can trace the wave's origin back to a specific patch of the sky, sometimes narrowing it down to a region just a few times the size of the full moon. This precise localization is what transforms a curious chirp into an astronomical event. It triggers an alert, sending coordinates to telescopes around the world and in space, telling them exactly where to point. Within minutes, optical telescopes search for a new speck of light, radio dishes listen for faint whispers, and X-ray observatories scan for high-energy signatures. This collaborative system turns individual ears into a sophisticated directional hearing apparatus for the entire planet. It allows the whole astronomical community to participate, translating a tremor in space-time into a full-spectrum portrait of the universe's most violent events. Our current catalog of cosmic chirps is just the beginning. Beyond the well-understood mergers of black holes and neutron stars lies a vast, uncharted territory of potential signals, whispers from phenomena so strange we have yet to even imagine them. The history of astronomy is a story of unexpected discoveries, and gravitational wave science is poised to write its most surprising chapter yet. One of the most intriguing hypothetical sources is the cosmic string. These are not strings in the everyday sense, but hypothetical, one-dimensional defects in the fabric of space-time, thought to be leftovers from the universe's earliest, most violent moments. Imagine a crack frozen into ice, but this crack is a thread of pure energy thinner than a proton and stretching across the entire cosmos. If these strings exist, their vibrations or sudden snaps would produce incredibly powerful and distinctive gravitational wave bursts, a sharp, singular crack in the quiet hum of space. Another potential source lies in the death of a massive star. While we see the brilliant optical flash of a supernova, the core collapse itself happens deep within, hidden from our view. The exact mechanism that triggers the explosion remains one of the great unsolved puzzles in astrophysics. A gravitational wave signal captured from such an event would be a direct broadcast from the heart of the cataclysm. It would reveal the precise choreography of the collapsing core, telling us if it formed a neutron star or a black hole in that first, violent second, and finally unlocking the secret of how a star dies. We can speculate even further. What if the vacuum of the early universe underwent a sudden phase transition, like water freezing into ice? Such a cosmic shift would have released an enormous burst of gravitational waves, a fossilized rumble from a time before the first particles formed. Or consider the possibility of gravitational atoms, hypothetical bound states of fundamental particles held together not by electric force, but by gravity itself. The whispers from such exotic systems would be faint, but they would carry the signature of quantum gravity, a theory that has eluded us for a century. Every time humanity has opened a new window on the cosmos, we have found something we did not expect. The gravitational universe is likely no different. The most exciting message we might ever decode is one we have not even thought to listen for. Even the most fleeting whisper can leave a permanent mark. After a powerful gravitational wave sweeps through a region of space, its work is not entirely done. General relativity predicts a subtle, lasting change, a phenomenon known as the gravitational memory effect. Imagine that ripple moving through a cloud of dust particles, all floating freely in the void. As the wave passes, it stretches and squeezes the space between them in its rhythmic dance. But when the tremor is gone, the particles do not snap back to their original positions. They settle into a new, slightly shifted configuration. The fabric of space itself retains a tiny, permanent scar from the encounter. It is as if the surface of a pond, after a large ripple has crossed it, does not return to a state of perfect flatness, but holds a minute, persistent dimple. This memory is a direct consequence of the universe's deepest operating principles, its conservation laws, and the fundamental symmetries of space-time. The energy and momentum carried away by the gravitational wave must be accounted for, and the memory effect is the permanent ledger entry, the proof that a profound transaction has occurred. Detecting this effect is one of the next great challenges in gravitational wave science. It would not be found in the transient chirp of a merger, but in the quiet aftermath, by comparing the before and after positions of the most stable objects we can find, like ultra-precisely timed pulsars, or by tracking the test masses in future space-based observatories. A confirmed detection would be a monumental achievement. It would provide direct, irrefutable proof of the non-linear, wave-like nature of gravity as Einstein described it. More than that, it would mean the cosmos keeps a permanent record. Every major cataclysm, every black hole merger, every neutron star collision would inscribe its signature directly into the geometry of the universe. These events would not just be moments we observed and recorded in our data, but changes that became a literal, physical part of the cosmic landscape, a history book written not on paper, but in the very structure of reality. The same cosmic structures that warp the paths of light can also bend the very ripples of space-time. This is gravitational lensing for waves, a phenomenon where the gravity of a massive object, like a galaxy cluster, acts as a cosmic magnifying glass. It does not just distort the light from a distant quasar, it can also curve the trajectory of a passing gravitational wave. Imagine shouting in a vast, echoing canyon. Your voice might reach a listener by traveling a direct path, but also by bouncing off a distant cliff face, creating a delayed echo of the same call. A lensed gravitational wave behaves in a similar way. The signal from a single black hole merger can be split, taking multiple paths around the intervening cosmic lens. Each path has a different length, so we would detect multiple copies of the same event, identical chirps arriving at our detectors days, weeks, or even years apart. These echoes are more than just a cosmic curiosity. They are a powerful new tool for measurement. Because the properties of the original wave are known from the first signal, the time delay between the copies acts as a precise cosmic tape measure. It gives us a direct geometric way to calculate the distance to the lensing galaxy itself. This provides an independent route to pin down the Hubble constant, the rate of the universe's expansion. Current methods for measuring this fundamental number are in a troubling tension, disagreeing on its exact value. Lensed gravitational waves could be the impartial referee, offering a completely new way to measure cosmic distances and resolve this outstanding puzzle. Furthermore, the way the wave is distorted reveals the total mass of the lens, including the vast, invisible halo of dark matter that surrounds galaxies. We could literally weigh the unseen by observing how it bends the fabric of space-time. This turns every massive object in the cosmos into a potential lens, allowing us to map the invisible scaffolding of the universe simply by listening to how it subtly warps the messages traveling through it. Gravity's own language is being refracted by the very structures it describes, creating echoes that illuminate the dark. Our most sensitive listeners are also tuned to a different kind of signal, one that never stops. This is the search for continuous gravitational waves, a constant, high-pitched hum from the universe's most perfect cosmic tops. The source is a spinning neutron star, a pulsar that is not perfectly round. If it has even a tiny mountain on its surface, a bump just a few centimeters high, its rapid rotation would make it an unwavering beacon of gravitational waves. Think of a spinning weight in your car's tire. A perfectly balanced wheel is silent, but the smallest imbalance creates a persistent, rhythmic vibration you can feel for the entire drive. A neutron star with a mountain is like that unbalanced wheel, constantly shaking the fabric of space-time as it spins. Detecting this signal would be like creating a gravitational map of the star's surface, allowing us to measure the height of these minuscule deformations on an object with the gravity of a sun. Yet, despite listening intently, we have heard nothing. The silence is deafening and profoundly informative. This absence tells us that neutron star crusts are not just incredibly dense, they are almost impossibly smooth and strong. The immense gravitational force crushes any potential mountain into a subatomic scale imperfection. The fact that we do not hear this continuous song places a severe limit on the maximum height of these mountains, telling us that the neutron star's solid crust can withstand unimaginable stresses without cracking or deforming. This silent data point is a crucial clue in the puzzle of ultra-dense matter, helping us rule out theoretical models where the stellar material is softer or more malleable. This principle extends to the grandest scales. The ongoing search for the stochastic gravitational wave background from the earliest universe also listens for a specific kind of cosmic static. Certain theories of cosmic strings or other exotic phenomena predict a loud, distinctive hum in a particular frequency range. When our detectors hear only quiet in that band, it is not a failure. It is a clear message that those particular models of the universe's infancy are likely wrong. We can confidently cross them off our list of possibilities. In the quest to understand reality, the universe speaks to us not only in the chirps and rumbles we detect, but in the very frequencies that remain stubbornly, meaningfully quiet. This fundamental silence from the cosmos speaks volumes, but the ultimate message gravity carries might be written in a language we are only beginning to decipher. The two great pillars of modern physics, Einstein's general relativity and quantum mechanics, stand in a state of profound tension. One masterfully describes the cosmic dance of planets and the bending of space-time on a vast scale. The other reveals the bizarre, probabilistic rules that govern the subatomic world. Yet these two theories refuse to speak to each other, offering contradictory pictures of reality when forced to meet in the most extreme environments, like the center of a black hole or the first moment of the Big Bang. This is the greatest unsolved puzzle in fundamental physics. The secret to a unified theory may be hidden within the very gravitational waves we are now detecting. At its heart, the conflict is one of smoothness versus graininess. General relativity paints space-time as a smooth, continuous fabric, a flexible stage. Quantum mechanics insists that at the very smallest scales, everything is granular, made of tiny, discrete packets of energy. So what is space-time itself made of? Is it smooth, or is it a seething foam of unimaginably tiny particles? If gravity is a force carried by a particle, like light is carried by the photon, then that particle is the hypothetical graviton. A gravitational wave, from this perspective, is not just a ripple, it is a vast chorus of these gravitons traveling together through the cosmos. Each wave is a quantum message written in the language of these fundamental particles. This is why studying the faintest whispers, especially the primordial gravitational waves from the universe's birth, is so critical. Those ancient tremors were born from quantum fluctuations, tiny jitters in the fields that filled the infant cosmos, stretched to cosmic proportions by inflation. By decoding their specific signature, we would be witnessing the direct link between the quantum world and the force of gravity, seeing how the tiny and the immense are fundamentally intertwined. Black holes are the ultimate testing ground for these ideas. Stephen Hawking showed that black holes are not completely black. Due to quantum effects at the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. This process creates a deep puzzle called the information paradox. According to quantum law, information about what falls into a black hole can never be truly destroyed. But if a black hole evaporates completely, what happens to that information? The gravitational waves from a black hole merger might hold the answer. The final, fading vibrations of the new black hole, its ring down, could carry an imprint of that quantum information, a subtle signature in the waveform that reveals how information escapes. Observing these mergers with ever-increasing precision is like eavesdropping on a conversation between gravity and quantum mechanics. We are listening for a faint accent in gravity's voice, a telltale stutter in the signal that betrays the graininess of space-time itself. To fully understand the stories gravity is telling us, from the softest hum to the loudest chirp, we may need to become fluent in the vocabulary of the quantum world, finally merging our two greatest descriptions of reality into a single, coherent story. Our current detectors are like microphones placed in a storm, catching only the loudest crashes of thunder. To hear the deep, quiet symphony of the cosmos, we must build a quieter and grander ear. The next great leap will take us off the planet entirely. The Laser Interferometer Space Antenna, known as LISA, is a planned observatory that will float in the void, a perfect triangle of 3 spacecraft trailing Earth in its orbit around the Sun. Each side of this triangle will be 2.5 million kilometers long. In the profound silence of space, free from the constant shuddering of our planet, LISA will tune into the low-frequency murmurs of the universe, a register of gravity's voice we have never before been able to hear. This is the domain of the truly colossal. LISA will listen for the slow, stately dance of supermassive black hole binaries, each 1 millionth of times the mass of our Sun, residing at the hearts of distant galaxies. These titans do not produce a quick chirp but a song that lasts for years, even decades. As they spiral together over millennia, their gravitational waves will create a continuous, rising hum. LISA will map their orbits with exquisite precision, tracking them like a cosmic conductor following a grand, slow-movement symphony. It will witness the final moments before these behemoths merge, events that will shake the very foundations of galactic cores. Meanwhile, back on Earth, a new generation of ground-based observatories is on the drawing board. Projects like the Einstein Telescope and Cosmic Explorer are third-generation detectors designed with unprecedented sensitivity. Imagine instruments with laser arms 10 times longer than LIGO, buried deeper underground in even quieter environments. Their advanced technology will reduce quantum noise to a bare minimum, allowing them to hear fainter whispers from farther back in time. The result of these new ears will be a transformation of our entire experience of the cosmos. We will move from catching occasional, loud events to listening to a constant, rich chorus. The sky, which now seems silent between major collisions, will be revealed as a vibrant ocean of ripples. These future observatories will conduct a detailed census of compact objects throughout cosmic history, detecting virtually every black hole and neutron star merger within a sphere of observation encompassing billions of galaxies. We will not just be hearing the universe's greatest hits, we will be tuning into its every whisper, building a complete sonic map of the dark, dynamic universe. These faint ripples are more than just messages, they are time capsules. Each gravitational wave we detect is a pristine artifact from a specific moment in cosmic history, carrying information that has traveled for millions or even billions of years completely untouched. Light from distant galaxies can be absorbed, scattered, or distorted by cosmic dust and gas along its journey, but gravity's waves pass through everything, delivering their data in an unaltered state. This makes them the ultimate tool for a cosmic archaeologist, allowing us to dig through layers of time and listen to the universe's formative years. The most ancient black hole mergers we can detect are like fossils from the cosmic dark ages. When the first stars and galaxies were assembling, the universe was a very different place. By catching the gravitational waves from the very first black holes that formed, we could learn about the conditions that gave them birth. Were they born from the collapse of the first gigantic stars, or did they form through other, more exotic processes in the dense early cosmos? Their masses and spin rates encoded in the waves are direct clues. A population of unexpectedly heavy black holes from a very early epoch would force us to rewrite our models of how the first structures emerged from the primordial darkness. This archaeological dig extends to the faint, collective hum of the stochastic background. That sound is not a single event, but the accumulated echo of every black hole and neutron star merger that has ever occurred throughout cosmic history. It is the fossilized record of stellar death across time. By studying the statistical properties of the individual events we are now cataloging, we can reconstruct the life story of the universe itself. The rate of mergers, the distribution of masses, these are all pieces of a grand puzzle. If we find that mergers were more common in the past, it would tell a story of a more violent, star-forming universe. A shift in the average mass of colliding black holes over cosmic time would reveal how the ingredients for these monsters changed as galaxies evolved. We are essentially taking a census of cosmic corpses, and from that census, we can infer the population of living stars that came before them. With every new chirp added to our collection, we fill in another blank in the cosmic timeline. Gravitational waves are not just signals from space, they are direct recordings from the past, a time machine that lets us eavesdrop on the universe's most ancient conversations. That faint flicker of light in a detector is the beginning of a story, not the end. It is a single whispered syllable in a language of mathematics and probability. Translating this raw data into a cosmic narrative is an art form in itself, a sophisticated digital archaeology that deciphers the faintest of echoes. The first and most crucial step is a process called matched filtering. The data stream from an observatory like LIGO is a cacophony of noise, a constant hiss from the quantum world and the rumbling Earth. Buried somewhere in that random static could be the signature of a gravitational wave. To find it, scientists create a vast library of millions of theoretical waveform templates. Each template is a predicted squiggle, a unique pattern calculated for a specific type of cosmic collision, with different masses, spins, and orbital configurations. The search algorithm then systematically compares every single template against the live data, sliding them across time, searching for a moment where the theoretical pattern and the real-world signal align. When a template matches the data with an exceptionally high correlation, it is like a key sliding into a lock. That is the moment of discovery. This is not a task for a single computer. This brute force comparison requires the power of supercomputers, often running for days on end, sifting through petabytes of information. Increasingly, machine learning algorithms are being trained to join the hunt, learning to recognize the subtle hallmarks of a signal amidst the noise, speeding up the search for these cosmic needles in a haystack. Once a signal is confidently identified, the real translation begins. This is parameter estimation, where we move from knowing something happened to understanding exactly what it was. Scientists use a powerful statistical framework called Bayesian inference. Think of it as a process of educated guessing that gets progressively smarter. You start with a prior belief, a set of initial assumptions about the source's possible properties based on our general knowledge of the universe. Then, you let the actual gravitational wave data update and refine those beliefs. The computer generates millions of potential waveforms that are consistent with the signal we detected, each one corresponding to a slightly different combination of source mass, spin, distance, and orientation. By running a colossal statistical sampling process, the algorithm determines which combinations of parameters are most likely to have produced the exact squiggle we saw. The output is not a single, perfect answer, but a beautifully detailed map of probabilities. We learn that the black hole had a mass of, say, 30 solar masses, but with an uncertainty of plus or minus 2. We learn its spin was likely high, and we can even visualize the most probable angle from which we viewed the collision. Every number comes with its own error bar, a humble acknowledgement of the limits of our measurement. This entire intricate process, from the first template match to the final probability map, is how we perform the modern-day miracle of turning a line of data into a concrete story. We transform an abstract flicker into a narrative about two black holes, locked in a final embrace a billion light-years away, their masses and spins now known to us with astonishing precision. The raw signal is the universe's untranslated message, and this is the careful, meticulous work of reading it aloud. Behind every cosmic whisper decoded is a chorus of human voices. The detection of a gravitational wave is not a eureka, a moment in a solitary lab. It is the culmination of a global effort involving thousands of scientists from dozens of countries, all united under the LIGO-Virgo-Cagra collaboration. This is science on a scale never seen before, a testament to what humanity can achieve when we focus our collective curiosity on a single, profound goal. When a promising signal triggers an alert, it sets off a meticulously planned chain of events that operates with the precision of a mission control center. Teams scattered across every time zone swing into action, working around the clock to verify the data, to rule out any possible terrestrial origin, and to pinpoint the location in the sky. There are stories of scientists being woken in the dead of night, of hurried calls and frantic typing, all fueled by the exhilarating possibility that the universe has just sent us a new message. But the collaboration does not stop at the gravitational wave community. The moment a signal is confirmed, an alert is sent out to astronomers across the planet and in space. This culture of open data and rapid communication is the engine of modern discovery. Within minutes, optical telescopes in Chile swivel to a new coordinate, radio dishes in New Mexico tune to a specific frequency, and orbiting observatories scan for X-rays. This entire ecosystem, from the laser labs to the mountaintop observatories, functions as a single, distributed instrument. It is a global nervous system for our planet, designed to listen, see, and feel the cosmos in unison. This grand endeavor reminds us that the quest to understand gravity's secret language is a deeply human one. It connects a programmer in Tokyo to an astrophysicist in Paris and a telescope operator in Arizona. It proves that our shared hunger to understand our place in the cosmos can transcend borders, uniting us in a common project that is both humbling and glorious. The ripples in space-time connect more than just points in the universe. They connect us to each other. This new sense of hearing the cosmos shatters an ancient, human-centric perspective. For all of history, we have been creatures of light, our understanding of the universe confined to what we could see. Stars were points of light, galaxies were swirls of it. We built our entire cosmology on this visual foundation, subtly reinforcing the idea that if we could not see a thing, it was not fully real in a cosmic sense. But the silent collision of two black holes a billion years ago forces a profound philosophical shift. The most cataclysmic events in the universe are often completely dark. They are silent in every wavelength of light, from radio waves to gamma rays, yet they roar in the language of space-time itself. We are no longer merely stargazers. We have become listeners in a cosmic symphony, and this changes everything about our place in the grand scheme. It confirms with stunning clarity that space-time is not a passive, abstract stage. It is a real, physical entity, as tangible in its own way as the air that carries sound. We are not just living on this fabric, we are embedded within it, and it vibrates with the motions of every mass within it. The universe is not a silent movie we watch from a distance. It is a resonant body, and we have just learned to feel its vibrations. What does it mean for our concept of reality when we can now perceive and measure an event that is utterly invisible? It forces us to expand our definition of what is observable. Reality is not limited to what emits or reflects light. The true substance of the cosmos, its mass and energy, and their most violent interactions, writes its history directly into the geometry of existence. This is a universe that communicates through its very structure, a dynamic, interactive medium where the planets, the stars, and the most exotic objects are all in constant, silent conversation, pushing and pulling on the fabric that connects them all. We are not separate observers looking at a distant cosmos. We are participants in this cosmic web, our very detectors stretching and squeezing as the messages pass through. To hear gravity's voice is to realize we are truly, physically connected to the most distant reaches of space and time, listeners in a conversation that has been going on since the beginning. The profound messages of colliding black holes would mean nothing if they remained locked in supercomputer databanks. This is the great challenge and responsibility of modern science, to translate these cosmic whispers into a story that everyone can understand. We rely on simple, powerful analogies to bridge the gap between the abstract and the tangible. That image of a trampoline bending under a bowling ball, or a ripple moving across a still pond, does more than just explain a concept. It gives the mind a place to stand, a familiar foothold from which to glimpse the strange geometry of the universe. These are not oversimplifications, they are essential tools that allow us to feel the reality of curved space-time in our bones. But the most powerful translation of all is sonification, the process of turning pure data into sound. When you hear that iconic chirp from a black hole merger, you are not listening to a simulation or an artist's interpretation. You are hearing the actual data, the precise stretching and squeezing of space-time, shifted in frequency so our ears can perceive it. The rising pitch is the literal sound of those black holes spiraling closer, the final crash, the moment of their violent union. This act of sonification transforms an impossibly faint signal into a visceral experience, allowing anyone, anywhere, to witness a cosmic cataclysm that happened a billion years ago. Making this science accessible is not a secondary concern, it is a vital part of the discovery itself. When a child hears that chirp and understands what it means, a spark of wonder ignites. That spark can grow into the curiosity that drives the next generation of physicists, engineers, and dreamers who will build the even more sensitive detectors of the future. It fosters a shared sense of awe, reminding us that these are not just discoveries for a select few, but profound truths about the universe we all call home. Effectively communicating gravity's secret language ensures its story becomes part of our collective human story, a narrative of exploration that belongs to all of us. That faint chirp echoing from a billion light-years away redefines our very presence in the cosmos. For millennia, we were merely stargazers, our understanding of the universe limited to the narrow band of light that happened to reach our eyes and our telescopes. We were passive observers of a silent movie, watching the play of stars and galaxies on a distant screen. But now we have stepped onto the stage. We are no longer just watching the universe, we are listening to its vibrations, feeling its tremors as they pass through our very planet. This act of listening transforms us from spectators into participants in an ongoing cosmic dialogue. We have become citizens of a much larger community, connected to the most violent and beautiful events across time and space by the very signals we detect. This new role is a profound paradox. On one hand, it is deeply humbling. Each gravitational wave signal is a reminder of our physical smallness, a message from colliding giants so far away that their light began its journey before our planet even formed. We are living on a pale blue dot, utterly insignificant in the vast scale of these cosmic forces. Yet, simultaneously, this knowledge is incredibly elevating. That we, with our fragile minds and temporary bodies, could build instruments of such exquisite sensitivity to hear these whispers is a testament to the awesome power of human curiosity and intellect. We have reached across the void with our technology and our reason, and we have understood a message written in the fabric of reality itself. This is the essence of cosmic citizenship. It is the realization that we are not isolated on Earth, but are woven into the dynamic fabric of a speaking, vibrating universe. We are learning to converse with the cosmos on its own terms, in its native language of geometry and gravity. Every time we decode a new ripple, we are not just collecting data, we are answering a call, affirming our place in a grand and ongoing conversation that began with the first tremor of the Big Bang. Our current catalogue of cosmic events is merely the preface of a much larger story, and the most thrilling chapters are still unwritten. Future gravitational wave observatories will turn their attention to the universe's most stubborn mysteries, starting with the true nature of dark matter and dark energy. We know these invisible components make up 95% of the cosmos, yet we have no idea what they are. Could dark matter be composed of a vast swarm of primordial black holes forged in the first second of the universe? Future detectors, by listening for the mergers of these ancient, low-mass objects, could finally provide the evidence. As for dark energy, the mysterious force accelerating cosmic expansion, gravitational waves offer a new kind of measuring stick. By tracking the precise distances to millions of merging black holes across cosmic time, we can map the expansion history of the universe with unprecedented accuracy, potentially revealing if dark energy's strength has changed over billions of years. Another profound question awaits us at the very limits of time. Can we detect gravitational waves from the first instant of the Big Bang itself? The primordial gravitational wave background is the ultimate target, a fossilized tremor from creation. Catching this signal would be like listening to the universe's first cry, providing direct evidence for cosmic inflation and revealing physics at energy scales so high they are forever beyond the reach of any particle collider. Such a discovery would open a window to an era before time as we know it even began. The very fabric of reality is also under scrutiny. Do wormholes, those hypothetical tunnels through space-time, actually exist? If they do, their formation or the passage of matter through them could produce a gravitational wave signal with a bizarre, unmistakable signature, completely unlike the clean chirp of black holes. Similarly, the search for exotic compact objects like boson stars or gravastars could reveal forms of matter so strange they defy our current classification. Each observation is a test, and a single anomalous signal could force us to rewrite the textbook. Could future waves even reveal extraspatial dimensions, a key prediction of string theory? If gravity is able to leak into these hidden dimensions, it would subtly alter the way gravitational waves propagate and how they ring down after a collision. Our detectors are, in effect, listening for the faint echo of a higher dimensional reality. The potential for a paradigm-shattering discovery is not a distant dream, it is the daily work of this field. Every new observing run, every more sensitive instrument, brings the chance to capture a signal that does not fit any existing template, a ripple that carries a message we have not yet learned to decode. The future of listening is boundless, a journey into a darkness we are only just beginning to illuminate. We have crossed a threshold in our relationship with the universe. The cosmos is no longer a silent, distant spectacle but a dynamic, speaking entity, and we have learned the first words of its native tongue. Gravity is the vibrant language, space-time the living parchment upon which its stories are written. From Einstein's solitary calculation predicting ripples a century ago to that first, fleeting chirp from a billion light-years away, we have unlocked a new sense. We are no longer just stargazers, we are listeners, feeling the vibrations of colliding black holes and the birth cries of neutron stars. This connection to the most violent and majestic events across time and space transforms our place in the cosmos. We are not just observing the universe, we are participating in a grand, ongoing dialogue. Let this profound shift inspire a deeper curiosity within you. What cosmic message will we decode next? What new story will whisper to us from the dark? Share your wonder about these mysteries in the comments, and join us as we continue our journey to the frontiers of space and science. The conversation has only just begun, and every new ripple promises to reveal a universe more strange and wonderful than we ever dreamed.